Welcome to this video instruction. It's about creating entities in Simio. So some of you may have already seen that there's a instruction manual online about how to create entities in Simio. And I also noticed that many of you are struggling getting through this manual. So this part is going to be about, this instruction video is going to be about creating your own distribution pattern for your assignment. And for this, we're going to be using software that's called EasyStat. It's really easy to use. And the good thing about it is that it's free to use as well. So let's get started and see if we can make some distributions of our own. So for this video, I'm going to work in Microsoft Excel to start with. And you'll see on the left a picture that should look familiar by now. And this is from your airport capacity lecture slides. And I took it from the PowerPoint presentation and copied and pasted it to Excel so I can use it as a quick reference. So just a quick look at this graph. How this works is that at 90 minutes before departure, so 1 hour 30 minutes before departure, 0 passengers arrive to the terminal. But then in steps of 10 minutes, at 1 hour and 20 minutes, so 80 minutes before departure, there are about, let's say, 0.075% of passengers arriving. So again, in steps of 10 minutes, at 70 minutes before departure, now 1 hour 10 minutes, approximately, let's say, 8 or 9% of passengers arrive to the terminal. So this is how this chart works, and we'll be using it later to create our own distribution. So far we've worked with integers to create our distribution. So for example, we said that at some point 4 passengers arrive to our terminal, then 3 passengers arrive, then 6 passengers arrive, then 1, and then 2, and so on. So for Simio to have some sense of time in the distribution, we don't need to provide Simio with the integer value. We need to provide the time that this passenger arrived to the terminal. So let's say this check-in opens 90 minutes before departure, and the first passenger would show at 90 minutes before departure. So again, we would have another passenger maybe showing up at 85 minutes before departure. We put in 85. So let's assume within the same minute another passenger arrives. So 2 passengers arrive at the minute 85. So we put in 85 twice. Let's assume another passenger arrives at the minute 83, and again at 82, and maybe again 2 passengers arrive at the minute 81, which means we need to put in 81 and 81. So this provides Simio with information about how passengers arrive to the terminal over time. And we use the minutes before departure as expression. Okay, so I'm going to delete this from the worksheet. The next step involved is to transfer the data from the graph to the worksheet. As an example, I'm going to do this for the domestic travelers, so following the blue line. And for this, I'm going to use shapes and then rectangle. And this rectangle I'm going to use as some sort of ruler. So now this is my ruler to move over the graph left and right. So this helps me to read off the values from the charts more precisely. So moving from left to right, the first data point that I'll find is here under 1 hour and 20 minutes. So that's 80 minutes before departure. And if I read out the graph, it gives me a number of about, let's say, 0.08%. It's a little bit of a guess, but ultimately we'll average out the values and we'll get to 100% in the end. Okay, so moving on to the next data point. And that's going to be here at 1 hour and 10 minutes. And the value there is about 0.09. So 1 hour and 10 minutes translates to 70 minutes before departure. The value 0.09. Okay, again, moving left to the next data point is going to be somewhere here. And so this is going to be for 60 minutes before departure. And I'm taking a value of 0.175 because it's right in the middle of 0.15 and 0.20. So the next data point is going to be the top when the most passengers arrive. This is 50 minutes before departure. And I'm going to set this value at 0.26. So again, moving right steps of 10 minutes, I'm getting to the next data point, which is just over 40. So this is 40 minutes before departure, and here I'm taking a value of 0.18% of passengers. Again, moving right, and I'm finding a value of 0.12. So this is 30 minutes before departure, 0.12. Moving to 0.20 is a value of 0.75. 0.75. Ten minutes before departure, we're going to see 0.04% of passengers showing. And that's also the last data point in this graph. So the ruler we don't need anymore, so I'm going to press delete. And actually I should have used a comma on my system instead of dots. I'm going to replace that with a simple function. Okay. So also we're going to have 100 passengers in this distribution. So it means that we're going to multiply this with the number of passengers. And then in this formula, I want to lock the 100 passengers and move this down. So this gives me the number of passengers, but do note that if I sum up this, I will get to 102.5 passengers. So obviously I wasn't very careful with reading the values from the graph, so I need to correct it at this point. So let's do that by changing these values manually. So obviously we can't have 17.5 passengers, so we're going to say that this is 18. And this is going to be 12 then, and this is going to be 7 passengers. So although the numbers are not even, we still have 2 passengers too much because we have a sum of 102. So let's correct this at the end. So we're going to say that this is 2 passengers, and obviously showing up 10 minutes before departure time is rather late. So I'm not at all happy with this distribution, but okay. For this example, we're going to go with it and not correct it. So to make the distribution over time, we need to correctly interpret the graph. This graph shows that the first 0.08% get to the airport between 90 minutes before departure and 80 minutes before departure. So let's say that the first passenger to show in our terminal might as well arrive at the minute 90, which is 1 hour and 30 minutes before departure. So we're going to set 90. So in column Q, we're just going to put the arrival times of all our 100 passengers. So between 90 and 80 minutes, I want 8 passengers to arrive. So almost every minute, passengers need to be arriving into our terminal. So we're going to skip 1 minute, and so we're going to see the passengers arriving at the minute 88, at the minute 87. There's going to be a passenger at the minute 86. Then there's going to be 2 at the minute 85. Then we're going to skip 84, and we have 83, 82. So we have just sort of randomly added 8 passengers to arrive between 90 and 80 minutes. So why is 81 and 80 not here? It's just because we don't see any passengers arriving in this example. And it may not be totally random, but I can ask Simio to fix that for us later. So let's prepare for the next step of 10 minutes. So we're going to work our way down to the minute 70, and until that time we're going to need 9 arrivals. So let's just say that there's a passenger showing up at 80, and then again at the minute 79, at the minute 78, 77, 76, 75, 74, 73, 72. And so these are 9 already. So basically I'm done, and I have no passengers showing up at the minute 71 or 70. Okay, great. So you'll see that the numbers are getting bigger. So for the next step of 10 minutes, we need to create 18 passenger entries. So again, we can sort of do this randomly. So let's say at the minute 70, there's 3 people arriving. And then at the minute 68, there is 2. And again, there's another one at 68. There's 2 that arrive at the minute 66. There's 4 that arrive at the minute 65. There is, let's say, 1 at 64, 1 at 63, 62. There's a couple. And 1 at 61. So let's see how many we got. So we got 18 exactly. So that's fine. Again, we need to do the same for the next series. So we need to do the same for the next amount of passengers, working our way down to the minute 50 and add 26 new passenger arrivals. So that's going to be the minute 60. There's going to be 3. Then there's going to be actually a lot of the minute 59. Let's also put in a lot of the minute 58. Let's put in some at 57, 56, 56, 55, 55. Some more at the minute 55, 54, 54, 54. Let's add some for the minute 53, 53, 52, 52, 51, and the minute 51 again. So this should all sum up to hopefully 26. Yeah, create another 26. Then we need to add another 18 until the minute 40. So let's assume that's 50, 50, 50, 49, 49, 48, 48, 47, 46, 45, 45, 44, 44, 43. Let's see how much we got. So we have 18 exactly. The next step is going to be until this, the minute 30. We need another 12 random. 40, 40, 40. We're going to have some at 37 showing. We're going to have some at 35 showing. 34, 34, 33, 32, 32, 32. Let's see how much we got. We got 13, which is actually one too many, so delete that. Until the minute 20 we need 7, and again until the minute 10 we need 2. So we're going to do these all in one attempt. 7 and 2. And we're going to have 26, 25, 24, 23, 22, 22, 21. Oh, that's actually one too many. Okay, 7. And then until the minute 10 we need another 2. So let's keep them close to the minute 20, because again otherwise they'll be too late and the check-in will be closed. So let's assume that this is for the minute 20 and then 19. So hopefully that would give me 100 passengers in total. So I'm just going to count the values here just to make absolutely sure that we have 100 and not one too many. But it seems to be fine. Okay, yeah, so we have 100 entities or 100 passengers in total in this distribution sheet. So this is my take of the arrival pattern for domestic passengers. It's not entirely random because I ran them from my head, but they'll make a pretty good distribution after all. Okay, so what we're going to do is copy and paste these values, all 100 of them, and we're going to place them in a software called EasyStat. Like I said before, it's free and it's very easy to use. So why not give it a try? And most of all, this is not something that you can do in Excel. So you need to have some other software to analyze this distribution and give us something to work with in Simio. So previously we may have worked with StatFit or with other statistical software, but in fact all would pretty much give the same sort of results. So before creating this video, I already downloaded and installed EasyFit. And when installing, it asked me to install the professional version or the standard version, and I chose the standard version. And so you'll find the download link in the description of this video. And just follow the instructions now and you will see how easy it is. So this is StatFit, and I just copied and pasted the values to my memory. So now I'm going to paste them back. And these are the exact same 100 values that I took from the Excel sheet. So what I'm going to do now is press Options and I'm going to set fittings. And I'm just going to see if all these are checked. So I'm just going to have a look at the general settings, make sure that the goodness of fit tests are all checked. Also make sure that the bounds are checked. So I've set my bounds, the lower bound at 0 minutes, and the upper bound at 150 minutes. So even if I randomly draw entities from this distribution, I could still get passengers arriving close to 0 minutes before arrival, just to simulate the fact that they may be arriving to the airport late for whatever their reason. Okay, so make sure to press save and then OK. Next, we're ready to analyze our numbers, and we can do this in two ways. Via the menu, click Analyze and Fit Distribution, or by pressing F9. This will open the Input Data tab, and here make sure that Continuous is checked, and everything else we're going to keep the same. Okay, so in the blink of an eye, EasyFit has created this histogram for me. Note that on the left are the observations, so the minutes that our passengers arrive to the terminal. So on the left closest to the check-in closeout time, and on the right is closest to the opening hours of the check-in counter. And these are the percentages that we also saw when we created our render numbers. Okay, so you will want to go to this tab, the Goodness of Fit tab. Here in this view you can observe how EasyFit has ranked according to these three tests. The Goodness of Fit according to these types of distributions. So we have 11 types of distributions which were tested against these three various tests. So observe that the best ranking is sort of this generalized extreme value distribution, and looking at the number 2 would be the Johnson SB distribution. The number 3 would be the log Pearson 3 distribution. Okay, so I already know that Simio doesn't know how to handle a generalized extreme value distribution, so we're not going to use that anyway. So we might as well go with the number 2. So do notice it's been ranked number 2 for these two types of tests, but not necessarily for the chi-squared test. So by clicking on the distribution name, it will take you to the detailed view. There's a few things here that we need to check. And first of all, we're checking whether EasyFit is not rejecting our test. And at the confidence level 0.05, this is not the case. And also observe that the p-value is always greater than 0.05. And this goes for this test as well as the bottom one. So p-value here is greater than 0.05. So all of these tests have not been rejected. We're happy with the p-values for 2. So that means we're happy to continue with this type of distribution. So from this point on, we're going to be working with a Johnson SB distribution. Okay, so there's another tab that we haven't explored. It's the Summary tab. And by clicking on it, it will take you to the parameter view of our various types of distributions. So we said that we're going to be working with a Johnson SB distribution, and here it gives all the parameters that are required to build our distribution. So in our case we have a delta value, a gamma value, and a lambda and xi value. So these are the parameters that we're going to be using to rebuild our distribution in Simio. So once you've assessed the parameters for the Johnson SB, there's one thing to do, and it's going to be under Tools, under Stat Assist, which really is a convenient tool to map your distribution pattern. So in here, click Johnson SB, and here we can copy and paste the parameters from the summary into the parameter window over here. So we're going to type in the value for delta, which is negative 0.11659. Then gamma is 1.5871, and then hit apply. So you can already see the shape of our distribution here. So the last ones we need to use for, so we're just going to continue with lambda, and we're going to set the value at 119.11, and the last one, xi, is going to be negative 68693 in my case. Then hit apply. This we don't need. I'm going to make that smaller. So you will see that now the bounds are also included. So basically what the bounds do is that it will set the scaling of this axis. So we'll see the first random number being sampled as early as -6, and the maximum bound is 119. So that's the latest random sampling that could happen, the minute 119. So effectively what this means is that the earliest passenger that can arrive to our terminal is at the minute 119, and the last passenger can show at a negative value of -7. So that would mean that it's after departure time of the aircraft, which of course is not very realistic. So we don't really want this number to be negative, because we don't want people to show after departure time, but we might still have people showing very late. So we're going to set this at 0. So the lower bound is going to be 0. And the maximum, so in our case it means that the earliest passenger can arrive 190 minutes. Okay, so even now we can play a little with these parameters, and they will show you how it will change the shape of our distribution. If we change the delta to 0.8, for example, and then hit apply, you will see how it has changed the shape of our distribution. Just make sure to set it back to -0.1. And we can do the same for gamma, and we can set this, for example, to 0. And also we can note how it will change the shape. So we're going to set this back at 5 and hit apply. And also note that this graph nicely corresponds with my data set. So I did indeed provide the data points for most of the passengers to arrive between the minute 90 and the minute 20. So this is nicely represented by this graph, but still there's an opportunity, because of the way I set my bounds, that passengers do arrive at the minute 0 or the minute 120. So you could play around with these bounds a little bit to manipulate your distribution. So for example, you could set it very tight to 19 and 19. And so we've now set the bounds to the highest bound, so the upper bound is now set to the highest observation. The highest observation was 90 minutes. The lowest observation was 19. So you'll sort of get a more squeezed distribution than before. So for now, I'm just going to set it back to 119 and 0, because I think I was very happy with that. So what this also shows is how to copy this distribution to Simio, and Simio is going to ask for alpha 1 value, alpha 2 value, and minimum and maximum bounds, and this is the way to transfer it. So exactly in this order. So our value for alpha 1 is going to be this value, our value for alpha 2 in Simio is going to be this value, but then note that the bounds are the other ways around. So we're going to use the values in the calculations tab, where it says that the minimum value is 0 and the maximum value is 119. Okay, so let's bring these values to Simio. So switching back to my model. So this is the model that I used for workshop 13, and you may have something that looks similar. And this may be very helpful to understand what's going on. So without giving much away for the next video, don't pay too much attention to what's given here, because it's all about establishing an arrival table, which we're going to do in the next video. But for now, I'm going to set my distribution to a random.johnsonsb. So in here I'm just going to type random dot, and while pressing the dot it already gives me all sorts of options that I have to enter distributions. So this is the one I was looking for, JohnsonSB, and like I said, it's going to ask for an alpha 1 value, in our case our delta value, alpha 2 is going to be our gamma value, and our minimum and maximum values. So we're just going to press this, double click, and so alpha 1 needs to have the value that corresponds with this. So -0.11659. 0.11659. Then comma. Then 1,5871. 1.5871. So note that I'm entering the values with a decimal point rather than a comma. And I differentiate between the values by using the comma. So make sure to do the same thing when you're doing this for your own distribution later. So we know that the minimum value is going to be 0 and the maximum value is going to be 119. Okay, just make sure that there's no spaces left. And so this is what we're going to enter, and just press the checkbox here. And now this distribution has been entered. Okay, so without giving a lot of details, I'm using an arrival table, and I have a flight that's scheduled to depart at 7:30 on the 6th of August 2016. So basically I'm going to change this to the departure time, 7. And obviously I would expect the first entities to be randomly sampled from the minute 0 until latest the minute 119. I'm going to leave this at 4 hours, and also I'm going to click on the output node of the source and put a breakpoint in it. So this will make sure that whenever the output source starts to create entities, it will hold or pause the simulation. Okay, I'm ready to run, and press the run button. So notice that the time is now starting. So we're into the first 10 minutes, nothing's happening still. So you can see the plot and what the plot is doing here. So now the simulation is on hold at the minute 7:55. So we're now 25 minutes into our simulation, and Simio is now randomly sampling from our distribution our first entity. Okay, so now what we'll do is delete the breakpoint and let it run until the end. So now pay attention closely to see what happens to the plot, and especially when the last entity is being created. So I asked Simio to create about 100 entities, so let's see when it will hit 100 entities. And remember that from the workshop, every box here, every label represents 5 minutes. Okay, so we're just going to pause the simulation when it gets to 100 entities being entered in our simulation, and we just want to know when that is. Okay, 10 more to go. We're now at 90, almost at 100. Okay, so 100 entities have now entered my simulation, and I've now paused the simulation. So let's have a look at this. So the last passenger was created at the minute 100, and this was done at about few minutes past 9, so 9:04 approximately, which is about 1 hour and 35 minutes after departure of the flight. So this corresponds to 95 minutes. So in our case, the last passenger was generated 90 minutes after departure, and whereas the upper bound was 119 minutes. So basically there's still 29 minutes that passengers could have been created but weren't by Simio in this particular case. And 90 minutes is still pretty close to my distribution, so I'm still happy with that result. I'm very happy with that result. Okay, so I can hear you thinking, why is he talking about passengers arriving after the flight? Because now, in the way that I set this up, everything is happening after departure of the flight. So what I want to happen instead is make sure that this deviation of how passengers arrive don't happen after departure of the flight, but I want it to occur before departure of the flight. So I'm going to multiply my distribution with the value -1 and then press enter. So now something will happen, as in the passengers will now arrive before the flight is set to depart at 7:30. It means I need to change my starting time of my simulation to 5:30, so I can simulate everything that happens before departure time. And then I'm ready to play this again. And again, I'm going to put a breakpoint on the output source and press the run button. So now that the pattern has been reversed because we multiplied it by -1, I would expect to see the first passengers arriving somewhere between the minute 119 before departure time, which we set at 7:30, and about 90 minutes before departure time. So I put the breakpoint on the output node, and the simulation is now paused at the minute 5:56. So this is only 25 minutes into the simulation, and consider that my departure time was set at 7:30. So this is now about 1 hour and 35 minutes before departure time. So this corresponds with about 95 minutes. So at least it's somewhere between 90 and 119, the value that I was expecting. And remember that this simulation is entirely stochastic, so I have no control over how Simio randomly samples these values from the distribution. Okay, so I'm going to take away the breakpoint and press run button. and I'm just going to wait and see when the last passenger is going to be created, and I would expect it to take place somewhere between 20 minutes before departure and 0 minutes before departure, so somewhere around 7:10. So monitor the plot and see how it's developing. Okay, passengers are now still being created, and now we hit about 100. So I paused the simulation. You can see that there's now 100 passengers in my system since I started the simulation, and the minute is now 07:07. So about 23 minutes before departure of the flight, the last passenger has showed at the airport. So I agree that this is more or less in line with the distribution that I entered, so I'm very pleased with this. Don't be worried too much if the setup of my source didn't make sense to you, because that is what the next video is going to be about. So if you haven't set up something similar like this, you could just put in this in the inter-arrival time of your source and try to simulate if this would work for you or not. Okay, so I hope this was helpful. If you have any questions about this video, post them in the comment section below.